This video is about the second derivative test. So if you don't know the first derivative test, you may want to go and remind yourself about that first. But let's just go ahead and get to it. The second derivative test for critical numbers. Assume that f of x is differentiable and let c be a critical number. If the second derivative exists, which by the way is no guarantee, because remember critical numbers are a first derivative feature, right? A first derivative phenomenon. Then if the second derivative is positive, that tells you something about whether the critical number goes with a local max or a min. If the second derivative is negative, that tells you something about whether the critical number goes with a max or a min. And then we also have to consider, what if the critical number also makes the second derivative equal to 0? So we'll get to that in just a second. So just a reminder, a critical number is something that makes the first derivative 0 or undefined. And the first derivative test is something that tells you whether critical numbers go with maxes or mins. So the second derivative test is also something that tells you whether critical numbers go with maxes or mins, but you're just using the second derivative to get that information. And in the first derivative test, you use the first derivative to get that information. So if the second derivative is positive, you may want to try to use what you know about concavity. So if you don't know about graph concavity as it relates to the second derivative, you may want to go find a video for that. The one on this channel is fine, or wherever. But think about what you know about concavity and then try to pause the video and see what this is going to say. Let's see if you can fill in these gaps, at least for the first two. Okay, so if the second derivative is positive, that means the graph is concave up. And if the graph is concave up, that means that it has to be a min if it's anything. And it turns out that's right. So if the second derivative is positive, then the y value for your critical number is a local minimum. And similarly, if the second derivative is negative, that means your graph is concave down. And if your graph is concave down, that means you're going to have a local maximum. So the benefit here is, unlike the first derivative test, you don't have to choose representative points and check on either side and then see how it changes. You're taking the critical number and just putting it directly into the second derivative and observing the sign. So it's a sort of more straight shooting, I guess. The downside is that if it makes the second derivative equal to 0, well, the graph is neither concave up nor concave down if the second derivative is 0. So this is inconclusive. So do something else, or in particular, maybe use the first derivative test, which will always work. Okay, so let's just see this in action. Analyze the critical numbers of the function. Use the second derivative test if possible. So analyze the critical numbers. Remember, that language usually means determine whether the critical numbers go with maxes or mins. So to start this problem, of course, we're going to need the critical numbers. So we're going to have to take the first derivative. So first derivative is 5x to the fourth minus 20x cubed. Critical numbers are things that make the first derivative undefined or 0. So is this ever undefined? No, it's polynomial. Again, I'm sticking with something sort of simple because we're sort of just trying to get a feel for the concept. So what we're going to do is take this polynomial, set it equal to 0, and solve. So in this case, I can factor out 5x cubed, leaving me with x minus 4. So then 5x cubed is equal to 0, x minus 4 is equal to 0. This gives me x equals 0. This gives me x equals 4. So my critical numbers are x equals 0, x equals 4. Okay, so now the question is, do these go with maxes or mins? So if I want to do the second derivative test, let me go ahead and just get another color because I've got kind of a lot written here. So the second derivative test says that I take my critical numbers and I plug them directly into the second derivative. Okay, so I'm going to take 0, I'm going to take 4, I'm going to plug them directly into the second derivative and see what they spit out. So I'm going to need the second derivative. So I've got the first derivative, which is 5x to the fourth minus 20x cubed. So then the second derivative is going to be 20x cubed minus 60x squared. Now, if I plug in 0, what am I going to get? 0. Womp womp. So I included one like this so that we can see what happens when we get inconclusive. So if you go back and look at the result, you might remember that when the second derivative is 0, that doesn't tell you anything. Okay, so that means we're going to have to do something else here. But for 4, let's see what happens. Right, if I plug in 4, right, I'll get 20 times 64 minus 60 times 16. And you can do the math here if you would like, right? But 64 is bigger than 60 and 20 is bigger than 16. So this is going to be positive. And again, I don't care what the value is. All I care about is the sign. So this tells me immediately, right, by the second derivative test, you may want to pause and answer for yourself or just answer it out loud right now at your computer. It tells me that f of 4 is a local, drum roll please, not maximum. Positive goes with minimum, right? Remember, positive means that it's concave up because we're talking about the second derivative. Concave up means it has a bottom, which means it is a minimum. Now, for 0, we're going to have to go back to the first derivative test. So we're going to use the first derivative test. So this will just be a nice reminder about what that is. So for the first derivative test, you might remember, you're going to make a number line, you're going to throw your critical numbers on the number line, and then you're going to choose some representatives here. So this divides up your interval from -infinity to 0, from 0 to 4, and from 4 to infinity. And then I'm going to just get some new reps to see what happens here. So my representative here maybe is -1, my representative here maybe is +1, and over here maybe it's 5. Now if you want, you can leverage up the information that says you know that 4 is a local minimum and sort of retroactively know what is happening in these two places, right? Because if you know that f of 4 is a minimum, minimums happen when you go from increasing to decreasing. So really the only one we don't know is this, but we already know that this is either neither or it's a maximum, right? Because of this negative sign. But we'll go ahead and just test them all. So x, f prime of x, I'm going to take my representatives, plug them in. Remember that the first derivative here was 5x to the 4th minus 20x cubed. So if I test -1, right, I'll end up with something positive. If I test +1, I'll end up with something negative. If I test +5, I'll end up with something positive. So first of all, our negatives were right? Negative, negative, or positive. Positive, not our negatives, but these two were correct. And then it turns out that this one was, in fact, positive. So by the first derivative test, what does that tell us about f of 0, the other critical number? It goes with which? A max or a min? It is a local increasing to decreasing means it was going up and then it started coming down, right? So that's a maximum. So f of 0 is a local maximum, and then based on our second derivative test work above, f of 4 is a local minimum. Also, just observe here, right, like getting the second derivative equal to 0 is truly inconclusive, okay? You don't know what's happening here. It's not like it's neither one. Using the first derivative test, we found out that it was supposed to be a max. You would never have known that from this. Okay, so if you want to use the second derivative test, it's great in that you don't have to choose representatives. You just take your critical numbers and plug them straight into the second derivative and look at the sign. But if you get 0, sort of back to the drawing board. Use the first derivative test instead.